let's discuss a concept, that of linear dependence, linear independence. So let's begin. Here we have an example. In the linear space R2, the vector 2, 4 is a scalar multiple of the vector 1, 2. Observe that 2, 4 equals to 2 times the vector 1, 2. Negative 3, negative 6 is also a scalar multiple of 1, 2. Observe that negative 3, negative 6 is equal to negative 3 times 1, 2. There are infinitely many such cases. There are infinitely many elements in R2 that are scalars of the vector 1, 2. There are some, however, that won't be scalar multiples of 1, 2. Observe, here 3, 5 is not a scalar multiple of 1, 2. Very simple to see. Try setting 3, 5 to equal a scalar multiple of 1, 2. What we want to find is the scalar. Is there a scalar C such that when you perform the product C times 1, 2, you get the answer 3, 5. Now, that will mean, of course, that if there was such a scalar, that would mean that 3 equals to C times 1, which is C, but at the same time, 5 equals to 2C. Now, of course, that is not going to be satisfied, because if you tell me that C equals 3, when you put it into the expression 2 times C, you end up with 6, not 5. So, no solution. I set up this equation trying to find C, and I determined there is no solution. So, that tells me that 3, 5 is not a scalar multiple of 1, 2. Now, let's rephrase some questions that we already asked. Okay, so I'm going back to the very first example, but I'm rephrasing. I'm writing it differently. Are there constants C1, C2 other than 0, 0, other than C1 equals 0 and C2 equals 0, such that the linear combination of 1, 2, and 2, 4 equals the 0 vector in R2? Well, the answer is yes, and you might suspect why it is yes. As we already saw before, 2, 4 is simply 2 times 1, 2. So 2, 4, see, if we already know that 2, 4 equals 2 times 1, 2, then if you want to form a linear combination of 1, 2, and 2, 4, you would like to put this on the same side of this equality. So you end up with negative 2. So I'm bringing this to the left. Negative 2 times 1, 2 plus 2, 4. I can view that as 1 times 2, 4. And that ends up being the 0 vector. Okay, so the answer is affirmative, and here is a reason why. Now, as it turns out, there are more possible solutions for C1, C2. For instance, I could have written something like 4, 1, 2, minus 2 times 2, 4. That also satisfies the equation. The trick here was for me to multiply both sides by negative 2. So negative 2 times negative 2 is 4, 1 times negative 2 is negative 2, and then 0 times negative 2 is still 0, 0. Okay, let's go to another example. Are there non-zero constants, C1, C2, such that C1 times 1, 2 plus C2 times 3, 5 equals theta, equals the 0 vector in R2. Okay, so this is connected to our example where we couldn't write 3, 5 as a scalar product of 1, 2 times a constant. So, but the rephrasing here is now slightly different. Can I solve this equation? C1 times the vector 1, 2 plus C2 times the vector 3, 5 equals the 0 vector. Can I solve? Can I find non-zero values? Are there non-zero constants, C1 and C2, such that this linear combination is equal to 0? So we're being asked to solve this equation for C1, C2. So as you can see, we can set up a system here, two linear equations, two variables. The augmented, when you set up your linear system, it will yield an augmented matrix. It's going to look something like this. 1, 2, 3, 5, 0, 0. Now, we're solving for C1, C2. So we are reducing this matrix into reduced row echelon form. Okay, let's try this. Eliminate these two. So take row 2 minus 2 row 1. So we're multiplying first row by negative 2. 2 minus 2 is 0. 5 minus 2 times 3, which is 5 minus 6, is negative 1. When you multiply 0 by negative 2 and you combine it with 0, you still get 0. Okay, let's do the following. Now eliminate 3. I'm going to use negative 1. I'm not going to change it to 1. So it's going to be row 1 plus 3 row 3. Row 1 plus 3 times row 3. So this time we're multiplying second row by 3. 1 plus 3 times 0 is still 1. 3 plus 3 times negative 1 is 3 minus 3, which is 0. And then 0 times 3 plus 0 is still 0. And then here we have 0, negative 1, 0. Last step. Get rid of that negative 1. Get rid of that negative in front of the 1. So you multiply row 2 by negative 1. So you end up with 0, 1, 0, 0, 0, 1, 0. Okay. So conclusion. I have found a solution to the system where C1 must equal 0, C2 must equal 0. So then what's the answer to our question? Are there non-zero constants, C1 and C2, such that the linear combination of the vectors 1, 2, and 3, 5 equals 0? The answer is no. Because when we try to solve for C1, C2, we find out that this only solution that can happen is when both C1 and C2 are equal to 0. Okay, so now what do these two examples lead to? they lead to this concept of linear dependence, linear independence. So in a minute we shall define that. So these examples illustrate the ideas of linear dependence, linear independence. So let's define those two concepts. Okay, so here we go. If U1, U2, and so on up to Un are elements in a linear space, such that a linear combination of those equals the zero element of this space, such that C1 U1 plus C2 U2 plus and so on plus Cn Un equals theta, has scalar solutions C1, C2, and so on up to Cn, some of which are not zero, then we say that U1, U2, all the way up to Un are linearly dependent. The example we had of that was this one right here. Here, in this example, 1, 2, and 2, 4 are linearly dependent. Why? Because I can set up this linear combination of the two to equal theta and find solutions C1, C2, some of which are not zero. Recall that I could use -2, 1, or I could use 4, -2. Those are non-zero solutions, C1, C2. Okay. If U1, U2, all the way up to Un are elements in a linear space such that C1 U1 plus C2 U2 plus and so on plus Cn Un equals theta is only satisfied by C1 equals 0, C2 equals 0, and so on up to Cn equals 0. In other words, all scalars C1 through Cn are all 0. Then we say that U1, U2, all the way up to Un are linearly independent. Our example of that was this one right here, where we had the vectors in R2, 1, 2, and 3, 5. When I set up my equation, C1 first vector plus C2 second vector equal to the 0 vector, the only solution that comes out of that is C1 equals 0, C2 equals 0. That makes them linearly independent. It is the word, the term dependent, independent is supposed to have some connection to the idea that one is in some way dependent on the other, or not. In this case, 1, 2, and 3, 5 are not dependent on each other. They're linearly independent. They're in some quality, they are not constant multiples of each other. But of course, here we don't deal with only two. We deal with n in general. We're encompassing the concept for a general setting. You have n elements of a linear space. You're going to say they're linearly independent if, when setting up your equation, there is only one possible solution. All the scalar coefficients are 0. Okay, let's take a look at the notes. There are some notes for this. So again, formal definition here, a definition of linear dependence. So you have a linear space and you have a collection of elements in the linear space. We say that that collection is linearly dependent if and only if, when you set up your equation C1 U1 plus all the way up to Cn Un equals theta, it has at least one non-zero scalar solution. Now, if you view solutions as tuples, C1, C2, all the way to Cn, at least one of those entries is non-zero, then you will say that this set is linearly dependent. Otherwise, if that doesn't happen, if all the coefficients, C1 all the way to Cn, have to be zero and nothing else, then you'll say that then the collection is linearly independent. Okay, so let's pick one of these to do. So let's pick a couple of these examples to do right now in this video. So the question is to determine whether the given collection is linearly independent or linearly dependent. Now, in our first example, we're looking at elements of R4. So let's try number 2. So in this case, I'm using horizontal notation for vectors in R4, excuse me. So I want to set the linear combination C1 U1 plus C2 U2 plus C3 U3 plus C4 U4. Okay, so I'm going to write this and I'm going to switch to the board after I'm done writing. So I'm forming my linear combination for example 2. And that equals theta, which in this case is going to be the 0 vector in R4. Okay, so here it is. That's my equation. I want to find whether C1, C2, C3, C4 must all be 0. If they're all 0 and nothing else satisfies, then they will be linearly independent. Now, this converts into a linear system, 4 equations, variables C1, C2, C3, C4, whose augmented matrix is just formed by the columns are the given vectors and the right side theta. So this is my augmented matrix. So 1, 1, 0, 0, 0, 1, 1, 0. Okay, so we're trying to find we're trying to reduce this matrix into reduced row echelon form. Now, there are two possibilities to the reduced row echelon form. Either I end up with the identity and something here on the right, or I end up with some reduced row echelon form matrix which is square and something here. If I end up with the identity, then a theory of systems of linear equations says that there is only one solution to this system, and at that point you must conclude that it is 0, 0, 0, 0, because that is a known solution. It is a trivial solution. If you put zeros all the way here and you add up zeros, you're going to get this answer. So C1 equals 0, C2 equals 0, C3 equals 0, C4 equals 0 does happen to be a solution of this equation. If that became I, then that would be the only solution. At that point you conclude this collection is linearly independent. However, if reducing your augmented matrix leads to a reduced row echelon form where J is not the identity, then that tells you that besides the zeros solutions, there's going to be other solutions. So I could I could just work this out. I could answer my question, linearly independent or linearly dependent, depending on whether my matrix has in reduced row echelon form I in the left column or not I in the left column. So if you get this, linearly independent. If you get J not equal to I, linearly dependent. So that's what I want to do. I want to find out if this square matrix, disregard the right column, is row equivalent to I or row equivalent to J. Now, theory of determinants tells me that if the determinant of this matrix is different than 0, then this matrix is row equivalent to I. However, if this determinant is 0, then this guy is row equivalent to a reduced row echelon form matrix whose last row is 0. So I now conclude that I don't have to do all this work of a reduction. I don't have to do this Gaussian elimination. I can just determine my answer by finding the determinant of this left column of the augmented matrix. So let's work for that. Let's find the determinant of this 4x4 matrix. I could use my formula for determinants and spend maybe 15 minutes doing the calculation. For the sake of brevity, in this video, I will actually use a computer, a calculator, to perform the computation. All I have to do is find a suitable determinant calculator. Okay, so I was looking for Symbol Lab. So we'll do a 4x4. So there it goes. So our first row, 1, 0, 0, 1. Our second row is 1, 1, 0, 0. Our third row is 0, 1, 1, 0, and our last row is 0, 0, 1, 1. Okay, so let's see what the determinant of that matrix is. Is it 0 or not 0? That's the only concern we have. Okay, we just found out that the determinant of our matrix is 0. So in conclusion, this is what happens, not that. Okay. So therefore, this collection is linearly dependent. Okay, so let's try one more of those. This time I'll just use the determinants. Okay, I think I could try one right now without using a calculator. It's a 1, 0, 0, 0, 0, 1, 0, 0. 0, 0, 1, 0, 0, 0, 0, 1. Okay, so this one will be easy because the calculation of the determinant there is extremely easy. Okay, so by the way, this was problem number 2, example number 2. Now I want to work out example number 1. So I'm not erasing everything. Okay, so these 4 vectors in R4 linearly independent. Okay, so I'm going to look at my coefficient matrix. I don't have to worry about the right side because I know what I need to do. I need to find the determinant of the coefficient matrix. So we'll convert this into a system of 4 linear equations in the variable C1 through C4, and the coefficient matrix, of course, will just be these columns in that order. So here's my coefficient matrix: 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. I want the determinant of it. Okay, extremely simple. It is actually the identity, so its determinant is just 1. That's not equal to 0. So that says that this matrix is rho equivalent to I. It's I itself. So there's only one solution to the system. So only one solution to the system that you obtain. You obtain a system out of this. So what could it be? Well, we already know that C1 equals 0, C2 equals 0, C3 equals 0, C4 equals 0 is a solution. So it has to be the only one this time. Conclusion, these fellows, that one right there, that one, that one, that one, are linearly independent. Okay, let's take a look. There are some other types of examples. So what about if your collection consists of polynomials? So now we're in a set of functions. Our space is a set of functions. So determine whether the given collection of elements in P3 are linearly independent. Let's try number 6. I'm going to set up the board. Okay, so we're asking, is the collection consisting of 1 plus x, 1 plus x squared, 1 plus x cubed, linearly independent? Okay, so I'm going to form the linear combination of the 4. So I have to say C1 times 1, which is C1, plus C2 times 1 plus x, plus C3 times 1 plus x squared, plus C3 times 1 plus x cubed equals to, in this case, 0 has to be the 0 function, which is just 0. The 0 function is just 0. Okay, so question right now is find C1, C2, C3, and C4. Solve for C1, C2, C3, C4. Now we know that a possible solution is they are all 0. So that we know. But are there other solutions besides 0, 0, 0, 0? So that's what we're trying to do. Now, so let's do the following. Let's distribute and combine like terms. So here I have C2 plus C2x. There we have C3 plus C3x squared. And there we have C4 plus C4x cubed. Okay, combine like terms. These are like terms, they're constants. So I end up with C1 plus C2 plus C3 plus C4 plus. Now, I only have this x, so plus C2x, plus I only have this x squared term, which is C3x squared. And finally, C4 x to the fourth, that has to equal to 0. Now, on the left side, I have a fourth degree polynomial expression. On the right, I have the zero function. In order for this to be the zero function, all coefficients in this polynomial have to be 0. So C4 equals 0, C3 equals 0, C2 equals 0, and then C1 plus C2 plus C3 plus C4 equals 0. Now, I already know these guys. C4 is 0, C3 is 0, C2 is 0. So I end up with nothing there. That's just 0 plus 0 plus 0. That's just 0. C1 plus 0 is C1. Okay, so I just found out that this collection of polynomials is linearly independent because the only solution there is for the linear combination of those is all scalar coefficients are 0, only solution. So conclusion, the collection that contains 1 plus x, 1 plus x squared, 1 plus x to the third is linearly independent. Okay, I think we have one more we should look at. Let's take a look at that very last example. Observe that this has 3 terms. One plus x, and then 1 plus x squared. So in this case, we're forming the linear combination C1 plus C2 1 plus x plus C3 1 plus x squared. Let me see if we have a solution on this note so that we can just okay. It doesn't look like we have solution to number 7. So let me set it up on the board. And then there is a remark here. I want to use that remark this time. So on the bottom. So let me prepare the board first to do to set up the problem. So this will be set up to number 7. Okay, so the collection happens to be 1 plus x, and 1 plus x squared. Okay, so I'm determining whether this collection is linearly independent. Okay, so for my linear combination, C1 times 1 plus C2 times 1 plus x plus C3 1 plus x squared equals to the 0 function. Okay, so I could do the same thing I did in the previous example. Distribute, combine like terms, set coefficients equal to 0, and solve for C1, C2, C3. But I have another way of doing this which can be more efficient. An alternative, more efficient method to establish the linear independence uses differentiation. Now, all we need to know is that polynomials are infinitely differentiable. If I know polynomials are infinitely differentiable, I can take this function on the left side and differentiate as many times as I want. On the right side, I can also differentiate because the zero function is differentiable. Its derivative is 0, its second derivative is 0, etc. So let's do the following. Let's differentiate here. So differentiate both sides. The derivative of c1, since c1 is assumed to be constant, becomes 0, plus here when I distribute, that becomes 0, and that becomes c2. So here the derivative is just c2. Better yet, forget this. Differentiate 1 plus x. The derivative is 1, so you get c2 times 1 plus c3. Differentiate the polynomial inside. 1 plus 2x. Okay. You probably don't see exactly what we're after, but we're after, remember, we're after this. What is C1? What is C2? What is C3? Okay, let's differentiate one more time. So forget about 0. 0 is, you can omit it. C2, the derivative of C2 is 0, so you can omit that. So you end up with just C3 times the derivative of 1 plus 2x. The derivative of 1 plus 2x is simply 2. Okay. Now, C3 times 2 is just 2 times 2C3. Now, think about the following. 2 times C3 equals 0. It automatically leads to C3 being equal to 0. Because 2 times a number equals 0, the number must be 0. Once you have C3 equals 0, take it and put it back into the previous equation. So that's 0 times 1 plus 2x. That's 0. So you end up with C2 also equals 0. And finally, take both of these values, C2 equals 0, C3 equals 0, put them in your original equation. So that's 0, that's 0. That completely goes away, so C1 equals 0 as well. Okay, so we found out that there is only one solution to our equation. C1 plus C2, 1 plus x, plus C3, 1 plus x squared equals 0. There's only one solution. C3, C2, C1 are all zeros. So conclusion, yes, this collection is linearly independent. Okay, so this video, that's all for this video. Thank you.